introduce Yuankun Xu, who is a postdoc at UC Berkeley working with Roland Bergman. Yuankun's work focuses on understanding surface processes, particularly landslides, using a suite of tools including remote sensing and GPS, field instrumentation, and numerical modeling. From 2017 to 2021, he worked on his dissertation at Southern Methodist University in Dallas, Texas, working with Professor Zhang Liu, who incidentally worked at the USGS Cascades Volcano Observatory for a number of years prior to that. And today he's going to be talking to us about remote sensing and hydromechanical characterization of landslides. So Yuankun, I'll let you take it away.
Yeah, thanks very much, John, for the introduction. I will just directly go ahead to present the work I've been doing. So the title of my presentation is Remote Sensing and Hydromechanical Characterization of Landslides. My name is Yuankun Xu, and I'm a postdoc at the UC Berkeley. Before I get started, I'd like to show a video to answer one question: why studying landslides is important. This was the 2019 tailing dam failure in Brazil. The whole failure process was captured on CCTV cameras. This single event caused 270 deaths plus $7 billion of compensation for disaster victims and caused environmental damage. Globally, similar deadly landslides are occurring every year from Pacific coast to Himalayan mountain ranges to volcanic mud flows at global volcanic hotspots. These landslide events have claimed thousands of lives every year and also caused billions of dollars of property loss across the globe. To reduce the hazards, we need to understand the landslide process. Towards this goal, there is a lot of work that needs to be done. But here today, I will only touch upon 3 of the topics. The first one is observation and monitoring of landslides using remote sensing. The second one is runout inundation, forecasting or handcasting for catastrophic landslides. And the third one is mechanical understanding of slow-moving landslides. So part 1, landslide observation and monitoring using remote sensing. In this presentation, I will primarily talk about offset tracking and the INSA methods. For offset tracking, it simply utilizes cross-correlation of 2 images to track the common objects on these 2 images and to measure its relative displacement. The accuracy could reach centimeter to meter level depending on the image resolution. Another method is INSAR, which similarly use repeat pass images, but you can focus on the phase measurement, which is a little bit more accurate. The best accuracy could reach millimeter to centimeter level depending on the coherence. With these remote sensing tools, what could we use them to do for landslides? Here I will give 3 examples to just demonstrate their usages. So the first usage is to discover and map landslides. We utilized about 7,000 sensors of ALOS2, and P-band UAVSAR data covering the entire West Coast to detect or identify large slow-moving landslides. And we were able to identify about 600 new large slow-moving landslides, which were not included in the USGS landslide inventory at the time, but now they are already included in the new version of the landslide inventory. Here on the right, I'm showing this figure just to kind of highlight that some large slow-moving landslides, they may not be clearly seen, at least for the boundaries. They may not be clearly seen from optical images in high resolution, but they could be more clearly seen using this SAR interferograms. Of course, you could also potentially using other data such as NetRDM high resolution to identify them. But one of the advantages of INSAR would be for these satellite images, once the satellite is launched, it would be have relatively low cost for you to get the images and get the data. And the second application or usage is to obtain 3D or pseudo 3D surface deformation. Here we utilize the optical tracking of Sentinel-1 optical Sentinel-1 radar images and Sentinel-2 optical images to get the real 3D deformation surface deformation field of this 2019 post-Clayton landslide event on the Oregon coast. And with these 3D deformation vectors, we're able to better understand the mechanism of why this landslide happened and how it was moving. And the third usage is to capture temporal kinematics of landslides. Here, the example is focused on the irrigation trigger landslides in a Washington desert near Hanford. It's like a eastern Washington part. This area is relatively dry, so most of landslides on a riverbank were triggered by irrigation water. Here, I'm kind of highlighting time series measurement from INSAR for 2 landslides. So these relatively dense, like every 12 days, you get 1 measurement. So this time series deformation allowed us to better understand how the landslide movement responded to water, like river water level changes at the landslide toe. So that was basically introduction to how or what we can do with this remote sensing measurements for landslides. Next, I will move to part 2 for one of its important applications, remote sensing of precursory or preparatory motion for landslide inundation forecast. So every time when this type of landslide disaster happens, we would be wondering one question: how could we foresee damage of an impending hailstorm failure to give an insight about like how large the inundation zone would be, so we could evacuate people in advance to save people's lives. Of course, for most infrastructure, the houses also, if they cannot be moved, then they would be somehow damaged. But at least we could evacuate people to save lives. So for that question, we have a potential solution which contains 3 steps. The first step is to locate the landslide source area from the surface destabilization or movement. And the second step is to use this surface deformation to infer its source volume. And the third step is using this source volume and then incorporating granular fluid models to evaluate or assess how large the inundation extent would be if it fails catastrophically. So now let's dive even more into the 3 steps. So step 1 is locate the source area from surface creep. To achieve this goal, we could use the inside of the tracking method, because these methods have relatively high measurement accuracy, which is also very important, because at a very early stage of landslide destabilization or failure, the motion could be very subtle. So we need some tool with high resolution to be able to identify them. And the second step is to infer a source volume using the remote sensing of field observed surface displacements. So the principle for this is basically volume conservation. Imagine incompressible fluids traveling through a confined tube. It has to move much faster in another section rather than the wider section. With the same idea, we could try to infer the potential beta depth of a landslide section based on its surface displacement gradient. Basically, the area with much higher displacement gradients would potentially have a much deeper depth. And the third step is to incorporate granular fluid modeling to evaluate how large the inundation would be if it failed catastrophically. And for this 3-step approach, the first step was to locate this kind of destabilizing or slowly creeping hail slopes. But why is that important? Because this snow movement or destabilization of hail slopes today might signify a disaster tomorrow. For example, the 2017 Shimo landslide in China, it started to slowly moving in 2014, and the movement continued for several years. In 2017, it failed catastrophically and evolved into a relatively mobile debris flow and killed more than 100 people right down the slope. Globally, there are also many more examples demonstrating that massive hailstone failures are commonly preceded by long-term preparatory motion. For example, the 2018 Marano landslide in Italy, INSAR captured some preparatory motion 2 years before the final failure. This is the aftermath of the landslide event. Another example is the 2018 Cardia Goldman collapse in Australia. INSAR captured the preparatory motion 1 year before its final failure, and this is the aftermath. Globally, there are many more examples, but I will not introduce all of them here. But the key message is that for many large hailstone failures, there are possibly, most likely, some preparatory motion in advance. How to forecast landslide inundation using preparatory motion? We already introduced this schematic 3-step approach, but how do we actually do it in practice? I will explain this using a recent example, which is the Chanch Ecuador landslide. Here on this figure, the red polygon outlines the source area of this landslide, and the green polygon outlines the inundation extent of this landslide event. When the landslide source failed catastrophically, it directly destroyed tens of houses on the landslide. Beyond that, it also evolved into a mobile debris flow and traveled about 3 kilometers downstream and destroyed another 14 houses in this area. These photos are just showing the captured damages on site. This is on the landslide here. This is somewhere here. It's basically debris flow run up on the road. Here's the area many houses were destroyed. Here I'm showing this damage again as observed by hydrology optical images. So for this source area, this was before the landslide event. This was after landslide event. For here, many houses were destroyed. This was before the landslide event, and this is after. We can see that many houses were totally submerged under debris flows. Did the INSAR capture any preparatory movement for this landslide event? The short answer is yes. Both descending and ascending Sentinel-1 INSAR temperatures captured accelerating movement 4 months before the final catastrophic failure. Here, these 4 observation points are from this for descending data. The 4 points are marked here. This is from ascending data going here because they're looking at a different angle. So the observed line of sight of information is one is positive, one is negative. Also at a much later stage, but still before the final catastrophic failure, hydrology optical images from planet labs also captured some small collapses and tiny debris flows near the headscarp. With these observations, we're able to kind of implement our forecast strategy. But here for this case, I probably just should call it handcast because it already happened. We're just looking backwards to kind of do the simulation. So the whole procedure would be we use both ascending and descending measurement to get the pseudo 3D surface deformation vectors of this when it was still creeping. And then we can use the volume conservation principle to invert for its basal thicknesses. This is the inversion results. This is the comparison, which is obtained through NIDA-DM differencing. We can see that they match fairly well, not exactly at every spot. But here I also want to explain that for the inundation modeling part, for try to estimate the inundation extent, the whole volume of this source area would matter a little bit more than the absolute depth at each pixel. And with this inverted landslide source volume, next step is to use the open source decrawl model to estimate how large the inundation extent would be if it fails catastrophically. So for the decrawl model, the simulated flow behaviors would be controlled by many 3 factors. The first factor is topography, which is pretty much fixed for specific landslide. The second factor is volume, the source volume. For this case, it's controlled by the inversion parameter F. So F represents the ratio between average subsurface velocity over the surface velocity. If we assume the landslide moves like in between a non-Newtonian flow and a rigid block, this parameter would be bounded in between 2/3 and 1. And the third factor is the mobility. In declaw, it's controlled by shearing, dilation, or contraction behaviors of the landslide material. If the initial soil porosity is much larger than a predicted soil porosity, during shearing, the grains would reorganize and kind of contract, which would keep up the pore pressure and lead to a relatively mobile flow. Conversely, you would need to a much less mobile flow. Based on a lot of USGS flume tests and also some real-world examples, this parameter is bounded in between minus 0.02 and 0.02. And next, I will just show one animation of the simulated results for the inundation extent. Here, I'm using the average volume and mobility as I just introduced for this modeling assessment. You basically have a range of values. Basically, you have minimum and maximum volume, or minimum and maximum mobility. But here, I'm just using the average one. Just give an example. In fact, this one also fits the data, fits the observation the best. So when the landslide fails, you first will form some several channels as the flows, and then they will merge together later and arrive at this point where 14 houses were destroyed in about 7 minutes. And after the debris flow event, there would still be some deposits left on the flow path. To account for the uncertainties, I also simulated a range of scenarios using minimum volume, maximum volume, low mobility, and high mobility. Specifically for this case, the volume didn't matter that much. The mobility, in contrast, mattered a little bit more. Here, I will just play all these 4 animations together just for comparison. As we can see, if it's highly mobile, you move very fast and reach this point in about 2 minutes. If it's less mobile, you will get to this point in about 12 minutes. Also, the different mobility would also slightly affect the deposit thickness and width along the flow path. And for this case study, very fortunately in a sense, we had some on-site videos captured by local residents when the debris was forming. We also had a LiDAR DM acquired after the event, so we're able to do some validations. Here, the different colors are showing different mobilities. As I just mentioned, the mobility would matter much more than volume in this case. Here, we only focus on average mobility. So at the checkpoint number 1 and number 2, the declaw simulated landslide velocities are about 3 meters per second and 13 meters per second, which match our observations fairly well. At checkpoints number 3 and number 4, we validated the deposit depths. So the simulated results are about 24 meters and 9 meters, which also match our observations fairly well. Similarly, we use the LiDAR DM results at the transects AA prime and BB prime to validate the inundation height and width. In short words, they also match the observations fairly well. So this is basically one example of how we deal with the Changchun landslide. But are there any other applications and implications? For that, we actually have another example, which is the Good Basin landslide in Washington. So this landslide complex is located right above a very popular campground. From historical archived on Google Earth images, we can see that this landslide complex has been historically unstable. We can see a bunch of historical debris flow events occurring at this site since at least the 1960s. Our recent observations from both LiDAR and radar images between 2017 and 2019 all showed that there had been quite some small failures occurring at the head scarp. So the question at that time was, if a portion of this landslide complex fails catastrophically, would it damage the campground? To assess that, we used this granular freedom modeling, still the declaw. We simulated the two groups of scenarios. The first group we use no mobility. The second group we use high mobility. And for each group, we use the six different environments from very small to very large, based on the material properties and also the perched groundwater, perched water depths at the site. This is the most likely volume. From our simulations, we can see that with this volume, regardless of mobility assumption, you would damage the campground pretty severely. So after the study, U.S. Forest Service and the Sinaguampi tribe established a 5.3 million project in 2021 to move the river. So this is a landslide complex. This is just a portion of it. There's more on this side. And this is the old river. Now they are constructing a new river here. It's already finished, I think, because the news was in 2021. So this project would have three benefits. One most important benefit is that they were concerned that the sediments being transported into the river channel to damage the salmon spawning ground, which is quite important food source and also economic source for the Sinaguampi tribe. So the first benefit is that you would stop sediments being continuously transported into the river. And the second benefit is that this would also reduce the erosion of the river, basically reduce the river erosion of the landslide toe to increase stability. And the third benefit is basically when small channel as the flow forms, you would first enter old river and then new river, it will be more difficult to reach the campground. So for the case I just introduced, especially for the challenge case, for this kind of catastrophic landslides, it's fairly straightforward to kind of, well, I probably should not definitely stay forecast because there are still some uncertainties, but at least following this trend, it's very straightforward. Normally start with slow motion and then it keep accelerates and then reach a point of catastrophic failure. This is for this type of landslides, but sometimes it gets more tricky. For slow moving landslides, for the slow moving ones, they might go through many years, like tens of rounds of acceleration, deceleration without reaching a point of catastrophic failure. So what causes these differences? To answer that question, I will move into part 3, what controls static creep of slow moving landslides. Here, I also want to explain that I just use a creep basically from a geodetic observational perspective. I'm just saying this going through some very slow motion. I don't really mean it in a mechanical sense because I don't think we are very clear about if they are just kind of frictional slip or kind of creeping behavior mechanically. So for most landslides, after the movement initiation, they will normally have two contrasting behaviors. The first type is to go through rapid acceleration and form debris flows. And the second time is to maintain steady slow motion. These two contrasting behaviors would correspond to drastically vary the risks and mitigation measures. And mechanically, it could be also very similar to tectonic faulting process. So understanding these two behaviors could also potentially give us insights about the frictional faulting process. So this motivated us to answer this question: what controls steady slow movement of these creeping landslides? We decided to approach this problem using ground instrumentation, and a great experimental site is the Slamagani landslide in Colorado because it moves very fast. So at the middle section, the average daily rate is about 1.4 centimeters per day, which provides certain advantages, especially considering the achievable accuracy of geodetic instruments. In other words, we wanted to move relatively fast, so we could capture some tiny signal at a high rate with our kind of existing geodetic instruments. First, we wanted to look into landslide kinematics from monthly to minute scales. To achieve that, we instrumented the relatively fast-moving middle section with a couple of sensors like accelerometers, creep meters, and swim meters. Here, these accelerometers at the head, middle section, and at the toe part, were actually deployed by Bill Schultz at the NanoSat Hydro program. And thanks, Bill, very much for your continued support on this work. By here today, I will only show the data from 2 creep-meters we deployed in 2021 because they had the best sampling rate and resolution, specifically 10 seconds in sampling rate and 3 micrometers in resolution. Here I'm showing a photo of the side boundary on NanoSat. So this is the stable ground. This is the NanoSat. It goes downslope this way. Because it moves fairly fast, there's like a very clear shear boundary, like with a crack. It looks like a natural strike slip fault. This is another photo showing one of the creep-meters that we deployed at the site. This is the shear boundary. This is the downslope direction. So for this type of creep-meters, we use the carbon fiber to connect the 2 endpoints. So the instrument itself would be relatively insensitive to temperature changes. Now let's look into the data. On a monthly scale, we're able to observe that at these 2 sites, they're about 400 meters apart. This section has been moving at a pretty much constant rate. There is some kind of acceleration in end of July, which was caused by a strong storm event. If zooming in a little bit more into daily scale, we could see some tiny fluctuations, which could be better seen if we just subtract out this linear trend. And we think these diurnal signals most likely were caused by temperature changes or air pressure effects. And if zooming in a little bit more into hourly scale, we start to see some very interesting snip jumps. They happen maybe a few 0 minutes, and the amount is very tiny. Here we just call them like NanoSat micro snips. Characteristics of these NanoSat micro snips. The most prominent feature we could directly observe is that they pretty much resemble the tectonic fault creep signal we observed. A good comparison I could make is to the observed fault snip after the 1987 superstition hails earthquake in California, because tectonic faults are much larger in terms of spatial size. So the creep events they generate also are much larger in terms of magnitude and duration. Here specifically, they are about 10 times larger than these micro snip events we observed at the landslide. And to have a better overview of these micro snip events, I just kind of separated each single one of them, like crop this part, and then put them all at the original point, like starting point. So we just put them in here, and then we can have a statistical kind of visualization of these creep events, like micro snip events. These are from C1 creep meter. These are the corresponding velocities. These data are from C3 creep meter. These are corresponding velocities. So the duration of all these micro snip events are between 2 and 10 minutes, and the snip amount was always less than the, half a millimeter. Statistically, they kind of follow a logarithmic distribution, which means there are way more small magnitude events rather than large ones, which is also similar to the distribution of earthquakes. And the temporal behaviors of these snip events. Very interestingly, we observed that it appeared to be at least at a C1 creep meter, it appeared to be more sticky during daytime rather than nighttime. Here on this uppermost panel, I'm only plotting the creep like micro snip events. If there are no micro snip events just continuously moving, there's no circle plotted. So we can see most of them appeared during daytime, but even at night, it was kind of stable, unstably moving because the velocities were always greater than 0. It means they are moving both during daytime and nighttime. In contrast, at a C3 creep meter, it appeared to be equally sticky for daytime and nighttime. Similarly, it has been constantly moving because the velocities have always been greater than 0. With these observations, we got to this question: what caused these episodic microsnips? So a good framework we could refer to is the tectonic faulting process. If using a similar theory, we could hypothesize that these microsnip events could similarly caused by small velocity weakening patches on a landslide snip surface, as I sort of showed earlier. At least from the surface appearance, it does look like a side boundary, does look like a natural strike snip fault. This theory could also kind of well explain the different behaviors observed at these two creep meters. Because they are about 400 meters apart, so localized the slope angles and asperities could cause them to have different behaviors. And mechanically, landslides often have the condition that involving dominantly clay materials, high pore pressure, and spatially small asperities. These all kind of match pretty well with the description of the kind of creeping section of the San Andreas Fault. So these are the kind of points that would favor the theory of the velocity weakening patches on the slide surface. These are the observations we already have. We are also doing some ongoing explorations. One of them is the using nodal seismometers to detect landslide quakes. The motivation behind this was if there are large snip patches on the slide surface, when they move, they might generate some landslide quakes. We want to see if we could see them. And we also deployed several GPS stations at different spots, trying to see if there's like propagation of landslide motion at a high rate or even along the transverse direction. If there's a much stronger friction at the side boundary, it might take a bit long. It might respond much later than the middle point. Here I will show some preliminary results from the seismic array. So here we did some analysis to do the landslide quake detection, which was data processing was mostly done by Yifang Zheng at Tongji University, who was a postdoc at UC Berkeley. So on the first day, when we deployed these seismometers, we did a hammer shots. These small triangles are the nodal seismometers. These bigger triangles are the locations we did a hammer shot. So we know the locations and the time we did this, so we could directly just calibrate and calculate the surface velocity. This is the seismic signal on the seismogram for the hammer shot. If it's within the array, it will just propagate to different stations. Here I'm arranging these stations by their azimuth angle. This is basically what it looks like on a spectrogram. Using similar idea, we use the STA over LTA ratio method to detect the landslide quakes. And here's one example of a potential landslide quake. This one we can see arrived at some points, some stations here first, and then propagates to other stations, which means it's within the array. And we can see this the spectrogram. The frequent bands are about 0 to 20 hertz, and the duration is about 3 seconds. We just did the detection, that's the quick detection across all the 25 days for our deployment, and we're able to find about 300 near array landslide quakes. Here, these triangles are still the nodal seismometers, and these color dots are the detected events. I color-coded them using the current state of these events. We can see they're kind of distributed randomly. Speaking of the date, here's they are the same events, but I color-coded them by the time of the day when they occurred. Still, they're kind of random, which also makes sense if you think the whole beta surface is heterogeneous, and any spot, if they have asperity, it could generate some detectable landslide quake events. So these are based on the preliminary results we have right now. Based on this, the conclusion we could roughly draw is that we were able to detect some landslide quakes, which kind of support the idea that maybe there are actually some shear weakening asperities on a landslide surface. So to kind of conclude on this stomach gunning experiment, so we're able to say that for slow-moving landslides, most likely still controlled by frictional snip, which means spatial asperities and stress condition would together control the behavior to be catastrophic or creep. Because this shear weakening asperity has a very interesting kind of feature is that they are conditionally stable. If you change the stress level, even though it was stably moving, they could have like a ruptured kind of slip behavior, which is basically similar as the creeping faults. And sometimes they have tremors, or sometimes they have just sudden small rupture earthquakes. So theoretically, for landslide failure forecast, we sort of have to monitor their precursory or prepared motion, but in the meantime, we need to pay attention to their stress condition as well. And the last part is basically summary and outlook. At the very beginning, I mentioned that landslides are ubiquitous deadly hazard across the globe. In order to reduce their hazard, we need to understand the dynamics. Towards that goal, I kind of touched on 3 topics. First, remote sensing observation of the landslides, route modeling and kind of handcasting of catastrophic landslides using preparatory motion. And the third part is mechanics of friction shearing of slow-moving landslides. This method and tools could use a bunch of other kind of hazards scenario for ground subsidence, tectonic faulting, or cascading compound hazards. And lastly, I'd like to thank my collaborators and co-authors for their great contributions for the work presented here. And I also like to thank my friends and colleagues who came out to Colorado and California to help with the fieldwork. That is all my presentation. Thank you very much. I'm ready to take your questions.